These are your 26A absolute value function notes. We are going to actually embark on 3 special types of functions. You don't have to write this part down. But these are functions that are not linear but have linear characteristics. So that's why they fall in section 2.6. They have a lot of the same characteristics of a line. So think of like slope and y-intercept, but these really don't have, they kind of break some of the rules of slope and y-intercept. So they look like lines, they follow a lot of the same rules as lines, but they are not really lines. So the first of which is absolute value functions. I'd like you guys to attempt these by hand first, and then tomorrow when we go ahead and correct these, I'll show you with the graphing calculator what it looks like. So a lot of similarities to a parabola and to quadratics. The only easy part that's a little bit different is finding the vertex isn't as complicated, and so it's a little simpler form of the equation. This really truly isn't a standard form by any means, but the letters A, B, C, and D are just in places of where we could put, we could do different things to the variable. So, you know, a line is just y equals mx plus b. But when you throw the absolute value symbol in there, and you take the absolute value of the variable, well, what if I'm multiplying outside and taking the absolute value, then multiplying? What if I multiply first and then take the absolute value? What if I add or subtract something after I do all the absolute value multiplying? What if I decide that I want to add or subtract inside first, then add or subtract after? So by putting those absolute value signs around the variable, it creates so many different options. So you won't see necessarily A, B, C, and D all the time, but they could typically be there. So the vertex is the only point that doesn't have symmetry, just like a parabola. Okay, and remember with a parabola, everything was squared. So every squared buddy, if I square 2, I get 4. If I square -2, I also get 4. So everybody has a buddy except for 0. When you square 0, it's just 0, lonely. Okay, well, the same thing happens with the absolute value. Every number, the absolute value 3 is 3, but the absolute value of -3 is also 3. So what that creates is a V-shaped graph. Okay, so numbers that normally typically would be negative here bounce back up because of that absolute value sign. And so what it creates is a V. So by the end of this year, guys, I'm hoping when I say absolute value, you think V. If you see a V graph, you think, oh, that's for an absolute value function. If you see the absolute value sign in the equation, I want you to think of V shape. And so it's a special type of piecewise. We're going to talk about piecewise last. It's just pieces of functions. So technically, there's 2 pieces. There's this piece, and then there's this piece. There's like 2 branches, but they're really 2 pieces of a function. A, B, or AB represents the slope of the branches. So I'm going to show you how we do these. The vertex is the tricky point that you just have to do the calculation for. After that, we can make a table of values, or you can just count slope. I really don't care. Slope is probably the easiest. The only thing you have to be careful of is when you count slope and you're counting at the V from the vertex, I go up and over, you're going to go up and over the other way. You actually have a positive slope and a negative slope at the same time. So you do have to change your over directions. These V's can flip upside down. So all of that has to be in consideration. A table of values will never fail you. Okay, you can always do a table of values. So it's sort of the 2 points on the left, 2 points on the right, but you need that vertex. The vertex, when we're doing the calculation, it's the stuff inside here, the absolute value equal to 0. Since 0 is the only number on the number line that doesn't have a matching buddy, we set that equal to 0. And that locates that vertex point. And then from there, we do to the left, to the right. You can use symmetry. You can count slope. Okay, they're always symmetrical because of that whole idea of the buddy system. So let's go ahead and get started here. So this first one, The order of operations, after you do something to x, the very first thing we're going to do, if you plug in a number for x, would be to add 1. And then after we added 1 to the variable x, we take the absolute value of it. And then after we take the absolute value of it, we multiply it by 2. And then after we double it, we subtract 3. And that's equivalent to your y value. Okay, so what does that do to my v? Well, let's just first start with that lonely point. The lonely point is when this thing is equal to 0. So if that thing is equal to 0, that's when x is equal to -1. So we solve this little tiny equation, and that gives me my vertex. What gives me the x-coordinate of my vertex? So my x-coordinate of my vertex is -1 something. The something is after you plug it in. So like we just went through, the order of operations, I'm going to add 1 to -1. That gives me 0. The absolute value of 0 is 0. 0 times 2 is 0. 0 minus 3 is -3. So the vertex is -1, -3. Now I just bounce back and forth using symmetry. Okay, so the next point I can do to the left would be -2 and -3. And 2 points to the right would be 0 and 1. 0 and -2 are going to be buddies because they're both 1 unit away from the vertex. And 1 and -3 are buddies because they're both 2 units away from the vertex. So it doesn't matter which one you plug in. You can plug in 0 or you can plug in -2. They're both going to give you the same answer. When you plug in 0 and add 1, you get 1. The absolute value of 1 is 1. When you plug in -2, you get -1, and the absolute value of -1 is still 1. So either one. 1 times 2 is 2. 2 minus 3 is -1. And then I can either plug in 1 or -3 for my next order pair. I'm going to go ahead and put those on the graph, though. 0, -1, -2, -1. And then I'm going to plug in +1 for the next point. 1 plus 1 is 2. Absolute value is 2. 2 times 2 is 4. 4 minus 3 is 1. I'm doing the math. I'm just plugging it in and doing the calculations. So 1, 1, and -3, 1. Now I have enough. I know that it's a V, and it's linear. Those points just guide me. We go connect and extend, and there's my graph. They are straight lines. They are not curved like a parabola. And then the other thing I just want to point out is that your slope is equivalent to 2, the number that we're multiplying on the outside there. So if I was starting with my vertex, this step cannot be skipped. Okay, that's how you get your vertex. So once I get my vertex, if I want to just count slope, I can look at the numbers out in front of these two. Now, it's not just the number out in front of x, because it could be out front of x outside of the absolute value or inside, so you got to involve both. But I go up to 1 to the right, and then I just know up to 1 to the left. Up to 1 to the left, up to 1 to the right. So you could count slope instead of doing the table of values. And I will show you how to put all this stuff in and figure it out using the graphing calculator when we check these things. It says to determine the domain and range. So for the domain, as I scan this graph from the left and to the right, all reals are on this graph. So my domain is all reals. My range, however, as I scan up and down the y-axis, I notice that there's only graph from that point up. And so that point is -3, so I say y, greater than or equal to -3, just like a parabola. Down below, I got these two function values. Find the value of f of -3. You could use your graph. -3 gives me 1. I could use the table. I have it right there, -3, 1. And I could use the equation. When I plug in -3, I add 1, I get -2. Absolute value of -2 is 2. 2 times 2 is 4. 4 minus 3 is 1. F of 7, the function for 7. I don't have it on the graph. I could kind of guesstimate on the graph. I don't have it in my table, so I'm going to use the equation. So I plug 7 in for x up in the equation. 7 plus 1 is 8. Absolute value of 8 is 8. Times 2 is 16. 16 minus 3 is 13. and just kind of look at your graph, I would think if I kept going, it would hit at 13, so make sense of it. Okay, let's try another one. So this time, very similar, but instead of having the 2 on the outside, I have the 2 on the inside. So what does that do? Well, there's a couple of things it does. I am going to add 1, I'm going to multiply the variable by 2, add 1, then take the absolute value. Whereas before, I added 1, took the absolute value, and then times by 2. So it changes things because you're multiplying first, then taking the absolute value. So it does have an effect on the problem. Same as before, we need to set this thing 2x plus 1, just the stuff inside the absolute value, equal to 0. Why? Because that's your vertex. Why? Because 0 is the only number on the number line that doesn't have a buddy. So it's the lonely point, and it's the lonely point on the graph. 2x equals negative 1, divide by 2, x equals negative 1/2. So I'm just going to make a quick table again. My vertex is negative 1/2 something. When I plug negative 1/2 in and do the math, negative 1/2 times 2 is negative 1. Negative 1 plus 1 is 0. Absolute value of 0 is 0. It's always going to be 0 because we solved and said what value of x makes that stuff inside 0, negative 1/2. So you can kind of skip all of that and just say 0, absolute value is 0, minus 3 is negative 3. So do you see what changed there? Same exact problem. The 2 is now on the inside. My vertex doesn't shift over the whole negative 1. Because we multiplied by 2 first, it got twice as big, which means I don't need as big a number to make 0. So I didn't move over negative 1 anymore. I'm at negative 1/2, negative 3. Okay, and then everything else is the same. I'm going to just go ahead and use slope this time. My slope is 2. Okay, if you don't believe me, you can plug in the points, but I'm telling you it's going to be 2. It's this number 2 times this number here. So up 2 over 1, still at the half mark. Up 2 over 1, and then I got to go the other way. Up 2 over 1 to the left, and connect and extend. So this is why they are studied in section 2.6. They have a rise and a run. They kind of have a slope. It's not a true slope because it ends up being a V, but it rises and runs in both directions equally. The domain here, all reals, because everything to the left and everything to the right, there's no gaps. There's no gaps in our data. This graph covers the entire x-axis. The range, however, there are gaps. We are not covering anything below negative 3 again, so the graph is from negative 3 on up, so my range is greater than or equal to negative 3. Well, what happens if we have a number on the inside and the outside? It's going to have an effect on both things. But if you look at the beginning, we talked about this being your slope. Okay, so it's not an m. There's no such thing as an m. There's 2 numbers there. So my slope is a negative 6. To have a negative slope, right, when you have a negative slope of a line, the line falls. When we had a negative a value with a quadratic, it was an upside down parabola. Same thing's going to happen here. Okay? The absolute value itself is going to be positive. This will always give a positive, but when you take a positive and multiply it by a negative, it's going to make every number flip upside down. So let's do the same thing we did before. We got to take the value 3x plus 1 and set it equal to 0. Do a quick little calculation, and x is equal to negative 1/3. That is the x coordinate on my vertex. I don't know why I'm making the table. I'm not going to use the whole table. If my vertex is at negative 1/3 something, when I plug negative 1/3 in, this whole thing turns to 0. Why? Because of this. That's why it's negative 1/3. It makes it equal 0. Absolute value of 0 is 0 times negative 2 is 0 plus 3. Okay, this thing is sort of our y-intercept. It's not really a y-intercept, but it does move my graph up 3 units. So it's like a transformation. It's sort of like our k value. It's how much we move up, how much we shift up. It's sort of like an h and k from quadratics. I move over negative 1/3, and I go up 3. Now to use symmetry here, I'm not symmetrical in my point. So slope might be your safer bet. You just got to be careful. When there's a number on the inside and the outside, you can count -6. So I'm going to go down 6. And I'm going to go over 1 whole unit, which would put me at a third still. Down 6. And over to that 1/3 spot again. So it's a very steep slope, which 6 is. It's going to be almost vertical. It's more vertical. It's rising or running. It's falling 6 for every one that it runs. The other side, I will run 6, and I have to move over 1 whole unit. I'm at a -1/3, so I'll be at another -1/3. Down 6 and over to that -1/3 again. Very steep upside down graph. Domain is all reals. This will continue. Both branches continue to the left and to the right. So the entire x-axis is covered. My range, though, is only including values from 3 on down. So that's y less than or equal to 3. If you don't like the idea of counting -6 slope, or you don't like any of that, go ahead and plug in your points surrounded this. However, -1/3 is not smack dab in the middle, so your points won't necessarily be symmetrical with whole numbers. The graph is symmetrical, but not with whole numbers. Whole numbers and fractions would match up. All right, one last concept. I'm going to throw inequalities in here. We've shaded with parabolas. We've shaded with linear functions. We just took a test over that. So now we're going to shade absolute value functions. This is the only special function that we do shade. When we get into the other two, we don't shade on those. But it creates not an above or below, but when you graph a V, it creates an inside and an outside like a parabola. So same concept. Let's find the vertex. I take that value. X minus 1 equals 0. That means when x is equal to 1. So my vertex is 1 something. When I plug 1 in, I get the absolute value of 0. 0 plus 2 is 2. So my vertex is at 1, 2. It's going to open up. My slope here is a 1. So I'm going to count slope. Nice 45-degree V. Up 1 over 1 to the right, up 1 over 1 to the left. Up 1 over 1 to the right, up 1 over 1 to the left. Connect and extend. Okay, now we look at the actual inequality. It says it's greater than or equal to, so it's solid. I'm going to leave it solid. We don't have to break it. And then pick a point not on it. We could use the greater than thing. It's going to be inside. But let's just pick a point not on it. Remember, that greater than thing doesn't always work. So if I check 0, 0, and I plug 0, 0 into this crazy function, the y value is 0. I'm testing, is that greater than the absolute value is 0 minus 1 plus 2. Now, a little bit more complicated than when we did this with lines. So let's take a little bit work here. Do 0 minus 1, and that's -1. Plus 2, I haven't taken the absolute value yet. What is the absolute value of -1? That's 1. Plus 2 is 0, greater than 3. That's false. I showed a lot of work there, but sometimes we hurry on that step and we make mistakes. 0 is not greater than 3, so 0, 0 is not a solution to this inequality. And 0, 0 is on the outside, so then all my solutions must be inside. Again, I'll show you a way to do that on your calculators when we correct. We don't do domain and range when we work with inequalities because it's impossible to name all the different ordered pairs. So we only do it when we have when we're not shading. So remember, solid or broken and then shade. That's it. So we have a worksheet. Good luck.